Okay, I'm wondering if you could indulge me a moment. I'm going to put up some t-charts, and I'm hoping you'll fill them in. X and 2 to the x. Negative 1, 0, 1. X, 3 to the x. Negative 1, 0, 1. X, 4 to the x. Negative 1, 0, 1. Okay, take a minute, fill out that chart, or those charts. Hey, welcome back. Um, so if I plug a negative 1 in there, it's 2 to the minus 1, which is the same as 1 half. If I plug a 0 in there, 2 to the 0 is 1. And if I plug a 1 in there, I get 2. And if I plug this negative 1 here, I get 1/3. If I plug a 0 there, I get 1. If I plug a 1 there, I get 3. And any thoughts on here? Yep, 1/4, 1 and 4. Now, why did I want to do this? Well, I'd like to discuss this general case where b does not equal 1. I actually want to say where b is greater than 0 and not equal to 1. Okay? So b, here's 0, here's 1, can't be 1, can be these numbers, and has to be bigger than 0. And nothing over here. Okay? This is what I'm talking about. Bigger than 0, not equal to 1, and these numbers. This base is bigger than 1. This base is bigger than 1. This base is bigger than 1. I'm not going to be seeing in our class negative 2 to the x. No, sorry. But you want to see a freaky graph, craft that, and then press zoom decimal. Okay? All right. Yeah, so what is it that I want to do here? I want to build a general case, regardless of the base value. Notice here, my base was 2. Look what values I got. Notice here, my base was 3. Look what values I got. Notice here, my base is 4. Look what values I got. So if you were going to tell me which ordered pairs were on this general graph, what would those ordered pairs be? This is the input, and that's the output. And this is the input, and that's the output. And this is the input, and that's the output. These are the ordered pairs from 2 to the x. But I don't want the 2 to the x ordered pairs. I want this general case. So instead of specific 2's here, or 3's here, or 4's here, I'm going to have b's. And it turns out these are the reference points for any exponential function. Oh, one other thing, by the way. Exponential functions have a horizontal asymptote at x equals 0. Now, it's at x equals 0 unless there's a transformation that moves that horizontal asymptote up or brings that horizontal asymptote down. Okay, but yeah, that's my general exponential. Y equals b to the x passes through negative 1, 1/b, 0, 1, and 1, b. We also know that this has a horizontal asymptote at y equals 0. And what am I going to do with that recipe? Well, if I see y equals 7 to the x, I know that this curve passes through negative 1, 1/7, 0, 1, 1, 7. And that's kind of powerful. It certainly allows me to say, hey, What about something more complicated, like y equals 2 times 7 to the 3x minus 1 plus 4? Did I mention we were going to be doing transformations today? Surprise! These are inside the function. So do they affect x's or y's? X is on the inside. Good. These are outside the function, and they do affect y values. In what order will I do these two? PEMDAS, that's right. I'm going to multiply the y's by 2 and then add 4 to the y's. Is that true for these x values? No. Inside the function is opposite land. I'm going to add 1 to all the x's and then divide all the x's by 3. Okay? So let's see what that looks like. We've got our reference points, -1, 1 over 7, 0, 1, 1, 7. And don't forget the horizontal asymptote at y equals 0. Because this is a y value, any of my y transformations need to be put here, 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 and also here. Okay, so I'm going to multiply all the y's by 2. And when I do, I'm also going to do one of these x transformations. I'm going to add 1 to all the x's. So I've got 0, 2 sevenths. I've got 1, 2. I've got 2, 4. And 0 times 2 is still y equals 0 for a horizontal asymptote. Nice. But I'm not done yet, am I? No, not quite done yet. I still need to divide the x's by 3 and subtract 1 from the y's. So if I divide this by 3, I still have 0. And I want to subtract 1 from this. 1 is the same as 7 sevenths. 7 sevenths, oh, I'm sorry, 2 sevenths minus 7 sevenths is -5 sevenths. Okay? And we don't need 2 commas. There we go. And the next point, I'm dividing all the x's. Why do I feel like I'm missing something suddenly? I added 1 to the x's and multiplied the y's by 2. I did. Yes, I did. Nice. And then I wanted to come back and divide the x's by 3. Yes, 0 divided by 3 is still 0. But I also want to add 4 to the y values. Okay. So I'm going to take this, and I'm going to divide by 3. I'm going to divide by 3. And I'm going to divide by 3. Okay. But at the same time, I have to add 4 to the y's. So 2 sevenths plus 4, 4 and 2 sevenths. And here, I needed to divide the x's by 3, got it, and I'm supposed to add 4 to the y's. So I have this point, I add 4 to that point, no, I had this point, I add 4 to that point, and I've got 6. And finally, with my third point, I was adding 1, multiplying the y's by 2, but then I have to come back and divide the x's by 3, and add 4 to the y's. So 4 plus 4, 8. All right, now, I think it's really important that we not lose sight of this. We applied this y transformation, but we still need to apply this y transformation. And so I get y equals 4 for the horizontal asymptote. All right, so y equals 4. We have exponential growth here. As we get bigger and bigger x's, the y values get bigger and bigger. Here we have 0, 4, and 2 sevenths. Here we have 1/3, 6. And here we have 2/3, 8. Okay, any questions? All right, well, let's do a couple practice problems. How about you do this one? Y equals 2x plus 1 power minus 3. Give it a try. Come back when you're done. Hey, welcome back. Did you use your reference points? Remember, y equals b to the x passes through negative 1, 1 over b, 0, 1, and 1b. Don't forget there's a horizontal asymptote at y equals 0. So any y transformations need to be applied here. All right, I subtract 1 from all the x's. I subtract 3 from all the y's. What about this 2, Mr. Kukla? Yeah, nothing whatsoever. Not doing anything with it. The only thing I'm doing with it is getting these points. These are the points that go with this function. Just like when we were first doing this back in August, the function y equals x squared versus the function y equals absolute value of x, I didn't have to square anything. I didn't have to find the absolute value of anything. All I need this for is to help me establish the reference points, maybe an asymptote, and the shape. As long as my b value is greater than 1, I'm thinking about exponential growth. Something that looks like this. And if b is between 0 and 1, like 1/3 to the x. Here my base is between 0 and 1. In situations like this, we actually have exponential decay, where our values are getting smaller and smaller. Okay. So, oh, and by the way, transformations can change these relationships. And what I mean by when I say that is, if I have something like y equals 3/5 to the negative x, that negative, that fraction between 0 and 1. Okay, so this fraction between 0 and 1 tells me I've got some decay going on. But here I'm supposed to divide all the x's by negative 1. And when I divide all the x's by negative 1, the graph does this now. So this alone, decay. This alone, decay. The two of them simultaneously, growth. Okay, so let's then take a look at our graph. We had subtracted 1, and we subtracted 3. Oh, what's our b here? Our base is 2. Like that. Okay, so 1/2 minus 3 is negative 2.5. Negative 1, negative 2, 0, negative 1. Remember, we still have a horizontal asymptote not at 0. Our horizontal asymptote is y equals negative 3. Because remember, this y transformation gets applied not just to these points, but to this y over here as well. I need to see to subtract 3. Here's my horizontal asymptote. And what do we have? 0, negative 1. I have something like this. Negative 2, negative 5/2, negative 1, negative 2, and finally 0, negative 1. Ta-da! There's my graph. It's even labeled. So, yeah, kind of need you to be wicked comfortable with this. So let's do another. How about y equals 2 times 3 to the x minus 4. Please graph that equation. Hey, welcome back. Did you use your correct reference points? They should be negative 1, 1 over 3, 0, 1, 1, 3, and don't forget the horizontal asymptote at y equals 0. We need to apply our y transformations to that. Outside the function, I see I'm multiplying all the y's by 2. And inside the function, I'm adding 4. Oh, I don't have any x's. So then I end up with 3 2/3, 4, 2, 5, 6, and y equals, well, 0 times 2 is still 0 for a horizontal asymptote. Okay, is this exponential growth or decay? Well, my b value is positive, bigger than 1, so I'm inclined to say growth, and since I don't see a negative x up here, only a positive x, I think this is exponential growth. Okay. All right, how about this one? Y equals 2/3 x plus 1 minus 4. We graph that one, and after this we'll move on. Hi, welcome back. Your reference points? Yeah, I know, right? Negative 1, 1 over 2/3, 0, 1, 1, 2/3. So here, I think I'm going to do the flip and multiply. And so then I'm going to have negative 1, 3 over 2, 0, 1, and 1, 2/3. I can see the y values getting smaller and smaller, which suggests to me a decay. And we see that here. Because our base is between 0 and 1, we should expect exponential decay. Cool. So this is inside the function. This is outside the function. I'm going to subtract 1 from all the x's, and simultaneously, I'm going to subtract 4 from all the y's. And what does that leave me with? Well, I'm going to have negative 2, negative 3/2 minus 8/2 is 5/2. Okay, there's one ordered pair. And then I've got negative 1, negative 3, and 0, negative 8/3. Am I missing something? No, I think that's it. Okay. Oh, horizontal asymptote. Where's that? Well, remember, the horizontal asymptote is y equals 0, and we apply any transformations, y transformations to it. So, good. This is less negative than that. This is more negative than that. All right. I'm asking myself that question because I was just about to draw. And generally when I do exponential problems, we have here a base that's bigger than 1. And so I usually draw just that shape and start labeling the points. But this is decay because this number is between 0 and 1. So I'm going to draw my exponential decay graph. Don't forget a horizontal asymptote. We know the horizontal asymptote is at y equals negative 4. And over here, we've got some points. Negative 2, negative 5 halves, negative 1, negative 3, and 0, negative 8 thirds. Okay. Does that make sense in the context of the problem? I think so. Well, wait a second. Shouldn't that be 9 thirds? Huh. And that, I think I made a mistake in one of these. Okay, let's try them again. I feel very confident about decay. So we have negative 1, 3 halves, because that's 1 over b. We have 0, 1, and we have b. We have 1, b, 2 thirds. And y equals 0, the horizontal asymptote. So I'm subtracting 1, and I'm subtracting 4. So here I'm going to get negative 2, 3 halves minus 8 halves is negative 5 halves. Okay, I'm going to subtract 1, and I'm going to subtract 4. And then here, 0, 3 thirds minus 12 thirds, 3 thirds minus 12 thirds is negative 9 thirds, I believe. Let's just check. 2 thirds minus 4. 4 is the same as 12 thirds. 2 thirds minus 12 thirds. 2 minus 12 is 10 thirds. Okay. Now I kind of want to compare these. This is negative 2.5. This is negative 3. This is negative 3.333. So we've got y values that get more negative. What about here? As x heads this way, the y values are going down. And here, when we subtract 4, I get that y equals negative 4 is what we have for a horizontal asymptote. There it is, y equals negative 4. If I then plot these points, negative 2, oh, these are negative numbers. Now, I was sort of stuck thinking in my brain that this was the y-axis, even though it's clearly labeled over here. This is not the y-axis. It is instead simply my horizontal asymptote at negative 4. Okay. Otherwise, I feel great about these points, and my graph will keep coming down. Nice. So what about this one? Y equals e to the x. Now, if I pull out my calculator, I see that there's this e to the x button here. And when I type in a 1, I get that's the approximate value for e. 2.71828, 1828. And now this, oops, to the x power. This is e because of Euler, E-U-L-E-R. Euler found this number in some very interesting natural occurrences that we're going to be talking about in this unit. And yeah, it's kind of interesting. So when I see e to the x, I know that graph of e to the x is going to be between 2 to the x and 3 to the x. A little closer to 3 to the x than 2 to the x, because this is almost 3. Fabulous. So all of these graphs have the same swoosh shape, unless we're talking about some sort of decay, which needs either a negative up here in the exponent or a base that's between 0 and 1. This is definitely bigger than 1, so no. Okay, and then transformation graphing, reference points. Sure, we said for y equals b to the x, we were going to have negative 1 over b, 0, 1, and 1b, with, of course, the horizontal asymptote at y equals 0. So when I now see something like y equals e to the x, my reference points are going to be negative 1 over e, 0, 1, 1e. I still want y equals 0 for a horizontal asymptote. All right. Yeah, I'm uncomfortable with these, Mr. Kukla. Make them go away. Well, in some respects, the reference graph is just that exponential growth. Negative 1, 1 over 2, 0, 1, and here 1e. Why is that 2? It's supposed to be. And don't forget to label, because I will mark the problem wrong. Y equals 0 is your horizontal asymptote. Okay, there's our reference graphs. Our reference graph for y equals e to the x. E to the x is exponential growth. This base is bigger than 1, so we're looking at growth here. Okay. Yeah, so I'm comfortable with this. Many students are not. And so instead of this, you might write 2.718. And over here, I get negative 1.367879442. So instead of using 1 over e, I could use that. Okay. Nice. So I don't particularly care if you graph with decimal approximation or you graph with the actual value e. What I would like you to do is please graph this for me. Okay, please graph that one. Oh, and you don't have to pause the video this time because I'm going to walk out and walk back in. Be right back. Need to get some water. Hi there, are you done? I hope so. I want to get going. So our reference points, negative 1, 1 over e, 0, 1, 1e. Don't forget y equals 0 for the horizontal asymptote. I see 3 transformations here, 2 that affect y values, 1 that affect x's. So I'm going to add 3, because inside is opposite land, to all the x's. With the y's, I remember I follow PEMDAS. I'm going to multiply all the y's by 2, including this one. So now I've got 2, 2 over e, 3, 2, 4, 2e. And y is equals 0 still works there. I still have to come back one more time and add 1 to all the y's, including that one. So I end up with 2 plus, comma, 2 over e plus 1. 3, 3, 4, 2e plus 1. And of course, y equals 1 for the horizontal asymptote. Now, I see exponential growth here. The base is bigger than 1, and I don't have a negative here. That negative shifts the graph right 3. This negative would reflect across the x-axis. Are you uncomfortable with these? Well, here's what I know. I know I have a horizontal asymptote at y equals 1. Furthermore, I know that this is exponential growth. There's exponential growth. Now, all the y values are above this line. Well, there's 2. Is it over here? Is it here? Is it over here? Yeah, so let's label our points. 2 over e plus 1. 3, 3. And here, 4, 2e plus 1. Yeah, perfect, exact. No need for decimals. But look, I'm a realist. I understand that most of you are not happy with that or that. And you would be much happier here writing 0.368. And here, 2.718. And you can use those. You could take this and multiply by 2. You could take this and multiply by 2. It's just, I find it's much harder to do because I'm working with those decimals instead of leaving it these ways. All right. You need to be able to graph e to the x. You need to be able to graph 2 to the x and 3 to the x. I would definitely expect a CFA to include that. Okay, that's the first half of this video. The second part is I want to consider some word problem formulas. You're going to see these formulas throughout the rest of the unit. This one is the most basic. It's annual growth or decay. R is our rate of growth or decay. And so, yeah, let's just finish the letters. T is time. P is the amount you start with, sometimes called the initial amount. Here it's a P because of the word principal. And principal is a finance term that means the amount of money you're starting with. A, I'm going to be saying A is the amount at time T. You know, so if I keep my money in that account for 10 years, this will be how much I have in the account after 10 years. Good. If I have a problem like this, I put $100. Grandma gave me to an investment which earns 3% interest for 5 years. How much will I have? At the end of those 5 years? Well, the amount of money that I'm starting with, that's P. My rate goes here, and I have a time to go in there. So A equals 100, 1 plus 0.03 raised to the 5, or 100, 1.03 to the 5. Remember, you've got to do that exponent before you multiply by 100. 1.03 raised to the 5th power times 100. I get 115.927. And since in this case we're talking about money, I feel much more confident about rounding that to 93 cents. Okay? So if I hold on to that money for 5 years, I'm going to have an extra $15.93 at the end of that amount of time. It doesn't seem like you're getting much interest on that, but that's actually a really good interest rate right now. Oops. Oh, I'm so sorry about that. Especially if you're worried I might be choking to death and you couldn't fix it. Oh. It went down the wrong windpipe. Okay. The other thing I want to say about these problems, please don't freak out about them. Because that last one, there we go. That last one is sort of indicative of the problems that you're going to see at the beginning of this unit, where we're just plugging stuff in. So, why don't you do this one? $500 invested. Ooh. No. Car. Oh, yeah. Graduation present car. And folks, bought you a car for $10,000. That's a lot of money. The car's value depreciates at 8% per year. What will your car be worth in 4 years when you're done with college? Okay, well, let's see. Ending amount, starting amount, rate, time. Oh. Not plus, minus, goes down. To the 4. So A equals 10,000.92 to the 4th. Okay. So 0.92 raised to the 4th, and I'm multiplying that times 10,000. I get the car's value will be a whopping 7163.93. Okay? I don't think this was an overly difficult problem because all I had to do was put the rate in there, the time in there, and the initial amount here. How would this problem be different if we said your folks bought you a car 4 years ago for 4 years ago, period. Today, it's worth $10,000. How much did they pay if inflation is 4%. Oops, I don't want 4. 5%. 5%? Oh, no. This goes down in value. Sorry, if the value of the car depreciates or goes down, the value of the car drops by 5% per year. Okay, and so what's different here is we want to know, we're told what it's worth now, and we want to know how much did they pay? What was the initial amount? So I'll plug my 10,000 in. This stays P. I have 1 minus 0.05 to the fourth. Okay, 10,000 equals P 0.95 to the fourth. So how do I solve this equation for P? Well, this times P. So to get rid of this stuff, I'm just going to divide both sides by it. So P is going to be 10,000 divided by 0.95 raised to the fourth. Okay, 0.95 raised to the fourth, and I want 10,000 divided by that answer. So it looks like your folks paid $12,277.38. That was the original value. I don't know if you have anything harder, like this hard. I don't know that there's anything this hard in the breakout room problems tomorrow. They're all pretty easy. So just because you see a word problem, don't freak out. These are gentle plug-in kind of problems. No special math needed. There are, however, some other formulas. This formula annual growth or decay. We've got this one. This is a special formula for compounded, almost always interest, compounded growth, where n is the number of compoundings per year. So, for example, I invest $100 at 3% compounded quarterly for 5 years. So I'm going to have A equals 100, 1 plus at 5%. 0.05. How many compoundings? Compounded quarterly, so n equals 4. Yes, I do have to put that in both places, and we want 5 years. Remember, tidy up what's in parentheses, then raise it to the 20th power, and then finally multiply by 100. Do not try and distribute that 100. You've got to do PEMDAS. Do what's in parentheses, then do the exponent, then do the 100. Why don't you type this into your calculator, and let's just make sure we all get the same number. I got 128.20 dollars. All right, and then we have a third form that is, instead of compounded a certain number of times a year, like if I'm talking about quarterly, then n equals 4. But if I'm talking monthly, then n equals 12. And if I wanted daily, n would be 365. Okay? Yeah, instead of that, what if I allowed my money to be compounded continuously? And for compounded continuous growth, that's this. A lot of things grow continuously. Populations are growing continuously. Whether it's a population of bacteria in our kitchen sponge, or whether it's the population of Tucson, whether it's the population of virus in our society. We see a lot of exponential growth here. Okay? All right. So, yeah, I think we should practice one of those, and then maybe we'll call it. Computers are infected with a black hat virus such that V equals 100e to the 4.6052 t. V is the number of computers infected, and t is time. This is how many computers were originally infected. But look, I don't actually have to do anything here. This is already built for me. I just have to use this model to answer their question. So, how about V of 1? Where do you find V of 1? And once you've found V of 1, tell me what V of 1 means in the context of this problem. Okay, I got 10,000.298. So what does this number mean? Well, time in years. It means after 1 year, 10,000-ish computers will be infected. Originally, there were only 100. A year later, there are now 10,000. Can you tell me when will 50,000 computers be infected? Okay. So where does this number go? Does it go in here for time? Does it go in here for number of computers infected with the virus? Where do we put that number? Yeah, I agree. Over here is 100 e to the 4.6052 t. If I divide both sides by 100, I get 500 equals e to the 0.4, e to the 4.6052 t. Now comes the question about solving this. And you know, the answer is I'm not really comfortable yet solving this. You may remember something like take the ln of both sides of that equation. Yeah, we're not there yet, huh? Unless you are. If you are, by all means. But I also know I can use my graphing calculator to find this. Okay? How am I going to use my graphing calculator? Well, think about what we're looking at. This is exponential growth. This is the horizontal line, y equals 500. And I'm wondering when these intersect. So I'm going to pull out my calculator. And in y1, I'm going to type in e to the 4.6052t. And in y2, I'm going to type in 500. I'm not going to do zoom standard. Look at my y max. I mean, that's not even the y max. That's just, I need to see that point. So I think I'm going to change my viewing window. I don't need negative time. I don't know if this is going to be from 0 to 10 years, so I think I'm going to leave that. There, oops. Sorry, 0 to 10. And then here, y minimum of 0, good, going up to at least 500. No, no. About 750 in steps of 100 graph. Nice. Exponential growth. Ooh, this was 0 to 10. I probably only need like 3. And so let's find that point of intersection. Second, calculate, intersect. Enter, enter, enter. And I get that value to be 1.349 years. Wow. In just over a year, 50,000 will be infected. Kind of scary. Anyway, this is the hardest pretty much we get in this unit. And right now, we're going to solve it on the calculator. Okie doke. All right, well, I look forward to seeing you in class, and I hope this introduction to exponential graphing with transformations, yes, you do need to know that reference graph, those reference points, that shape, and don't forget the horizontal asymptote. You also are expected to know all those formulas. In fact, there's even one more. And here's the last one. Y equals a times b to the x. Sometimes I use this one when I want to write the equation of an exponential curve or graph. Yeah. Oh, and one other thing. Remember how we talked about this? A equals p e to the rt pert. Yeah. So we have some variations on that. P equals p sub o e to the kt. Q equals q sub o e to the kt. All of these are identical. This always stands for how much you end up with. This always stands for what you started with. And whether we write an E, an R, or a K, that's our growth or decay rate. All right? So please know your formulas. You'll be much happier if you do.